So my subject is on something very different, as you can see, but think of this as health monitoring of the Earth. It has a lot to do with that. So my subject today is about sensing soil moisture. This is a project that we have been working on for, let's see, this works great. We have been working on since 2006. It's been 7 years and counting. It's been funded by NASA, and over the years, we have accumulated a large team of researchers, mostly our students. Some have gone on. Why do we care about soil moisture? Let me give you a bit of background. I didn't know this before I joined the project. Turns out soil moisture data is one of the most important indicators in a range of things: agricultural drought monitoring, weather forecasting, and so on. And so this is something that NASA is very interested in. It actually is a data input type to a lot of its models. You can see climate, carbon, weather, water, and so on. The traditional way, soil moisture data is collected using remote sensing technology. So these are radars and radiometers on board satellites, and it flies through and takes, basically beams down and takes measurements. The feature of remote sensing is it has very large footprints, and so it is scalable in that sense, but it's very coarse-grained. The state-of-the-art satellite that NASA has will give us footprints about 1 square kilometer. And the problem we have is that because there's no ground truth, we don't really know how to calibrate or validate remote sensing. So you collect this data and you would like to believe it is representative of some mean of a certain field. But without a ground truth, we don't know how to validate that. And so that's where this project comes in, is to actually collect high quality in real time, near real time, in-situ sensing, using in-situ sensing to get ground truth. How do we do that? Typically, it is done by pick a spot, and then you dig a hole up to 2 meters deep. This is the well-shaped, and then you try to keep a very good vertical surface, and then along the surface you insert these soil moisture probes, the picture shown here, sideways into the vertical surface. Try to disturb the soil as little as possible, so that's how we do it. So then for each lateral location, you get about 8 to 10 in an all-out experiments. We do about 3 these sensor readings. These soil moisture probes are activated using a ground actuator module. And then from there, you can wirelessly transmit it. So that's how typically in-situ soil moisture data is collected. The overall system architecture that we envisioned was, so you have this unattended field data collection. Okay, consists of multiple of these lateral points, a certain number of soil moisture probes placed vertically. And then the data is collected at some base station in the field or on the side of the field, and then using 3G data solutions to remotely log the data onto our server, and that can be retrieved in real time. There are many challenges in realizing this type of system. I'll just name some of them. One is we would like the operation to be in real time. And we also need to cover a very large area. So, the data transfer has to be done wirelessly, because the networks are unattended, and oftentimes these networks are deployed in really out in the field without any infrastructure. So we really need to come up with very good energy efficient solutions to operate the system, so that the network can last as long as we need it to. Cost needs to be low, and the cost is primarily labor cost. The installation of each lateral location is very, very labor intensive, as I will show you a bit later in the presentation. So you want to select where you place these sensors really judiciously. we need a system to be highly reliable. That puts a lot of burden on system design and implementation because most of the time it's 100%. We cannot have the system next to our lab or next to our university campus. It's usually at least 4 hours drive, and one of the locations takes about a day to get to, by air and then in car and so on. So it has a very high burden on requirement of system reliability. And last but not least, scalability in setting up and operating the system in terms of deployment. Within that context, I'm going to focus on 2 things in this talk, and even that I'm probably only going to be just touching on the surface of this. So our project's gone along 2 directions. One is more theoretical explorations, in which we look at what is the best way to schedule measurements. Okay? And this is where we link the physical model with optimal control to basically try to reduce the sampling rate that the system has to operate at in an attempt to reduce energy consumption. Because when the system is not sampling, you can just shut it off. Things that we also looked at, which I will not actually get into in this talk, also includes sensor placement. How do we pick the best locations to install these sensors, and how to build a landscape simulator. This is actually not my area, but this is very much part of the project, so that we can make sense of the data that we collect and then work towards the ultimate goal of validating and calibrating the remote sensors. The other direction that we have been actively working on is system deployments. And as I will show you in the second half of the talk, this is very much a growth experience for us. We have gone through a couple of generations of design approaches, and I'll share some of our lessons learned with you, and you might find that interesting or instructive for your own project. So the measurement schedule, let me get to the first one, sensor measurement scheduling. The problem is that, more specifically, the problem is that, let's say I have multiple lateral locations fixed, and along each lateral location I have a fixed number of sensors that's installed. They are actuated, as I said, by this ground actuator. The key observation here is within a certain region, depending on the soil type and the ground cover, you would expect the soil moisture readings to be temporally and spatially correlated. So if there's a rainfall event and all my locations are within a few square kilometer region, then you expect them to be temporally, to be spatially correlated. Okay? And then temporally correlated because of the dry down, the rainfall, and so on. The exogenous forcing events. So the goal is to make the best estimate of the soil moisture evolution with as few measurements as possible. And this can be formulated as a centralized control problem. Conceptually, this is a rather standard exercise, but in reality, this involves a large amount of integration. Let me show you the different components of this control architecture. So you take the physical model, which describes the soil moisture evolution, and in reality, this is not a simple mathematical expression or set of expressions. This is actually given by a large simulator itself. And then you take the measurement model. This is basically what we collected in the lab, trying to look at the best way to describe the soil moisture. What's the input and what's the output? Linking the two. And these two combined get put together and generates essentially a transition probability, right? And that gets fed into a control formulation. From this step on, it becomes rather standard. And from there, we can generate optimal scheduling estimation policies. Even so, there are a lot of approximation and simplification assumptions we have to make. Let me give you a sense of these different components. The first is the physical model of soil moisture evolution. The picture here basically shows some example of the temporal evolution of soil moisture. This is in time, and you can see this is typical of a rainfall event because exogenous forcing, and then you have this dry down period, water gets dissipated, and the actual evolution is heavily dependent on vegetation cover, soil topography, and so on. And this shows the evolution in terms of depth. So this is the ground level, and this is going down deeper into the soil. So you can see, depending on the level of depth you are at, the mean over time is different. Okay. So the modeling methods is typically modeled as a pair of partial differential equations for flat surface, and when you have topography, there is lateral redistribution of soil moisture, and this is being used by hydrologists, this technique called triangulated irregular network surface model. So all said and done, at the end of the day, what you have is a large simulator that takes in hundreds of inputs. And these inputs include some randomized version of exogenous forcings, vegetation cover, soil type, topography. Fed into the simulator, and what the output of the simulator is, it will basically give you the temporal evolution of soil moisture for any given point in a particular region. That's being simulated. Okay? Now, the measurement model is collected using the specific instrument that we have in the field. This is a capacitance-based probe from Decagon. It collects fairly localized measurements and has shown to be very stable. So basically what you do is you collect a bucket of soil from the field that you're going to deploy this. You want this to be consistent. You bake it in the oven, completely dry it. Then you start adding precise quantities of water into the bucket. And every time you do that, you use this probe to collect the soil moisture reading. And this is how you calibrate the moisture flow. And then you basically get this curve fitting that we take as the input-output relationship of this measurement. And that gives us the measurement model. So now I have these two components. There is a physical model that tells me what the soil moisture evolution is, even though it is in numerical form, and then I have this measurement model. So when I put these two together, actually the first one is going to give me essentially a transition probability matrix. So basically what it says, if the current state of soil moisture is such at this level, what is the probability distribution over the next 10 minutes later where the soil moisture level is going to be. Okay? Standard transition probability matrix. That gets fed into a control formulation without going into, I see, going from Mac to PC, I'm losing some funds, but the basic idea is, this is actually fairly standard. We model the soil moisture evolution as a discrete time, discrete value stochastic process, given by X. And what we are trying to come up with is a measurement decision U, and this is a binary decision. Either I take a measurement at the next decision epoch, or I don't, I skip it. And if I do take a measurement, I get an observation one. And then what I do then is I take all past observations and past decisions to construct an estimation model. So I want to estimate what is the true state of the soil moisture process, and then I take all past decisions, past observations to make a decision as to whether I want to take a measurement in the next step. Again, the reason I do this is you can easily imagine if I am in a dry down period, then there's very little change in the soil moisture evolution, and so I don't want to take measurements every step. And typically, in our context, the discrete step size is about 10 minutes. You don't have a rainfall event. That's considered as good as continuous sampling. Okay? And then you construct this essentially cost function. This is an infinite horizon discounted cost that is penalizing the, this is my scheduling policy, so this is the cost of taking measurements, and the second term is essentially a penalty term on the estimation error. Okay? Again, this is fairly standard, and then from this point on, if we assume approximate the underlying system as a Markov system, Then this gets turned into a partially observed local position process, and then we can numerically compute the solution. The scheduling policy and estimation policy, here's an example of what the policy looks like. You basically have these orange vertices. These denotes the state of the system. These basically quantize these because this is a palm DP. The state of the system is actually probability distribution. So these are basically quantized. And depending on which state you are at, you make a decision as to whether a measurement is taken or not. Here, red denotes no measurements, and if there's no measurements, you transition next time into the next state of the system. And this is your estimated, the best estimate, essentially conditional expectation. And at the next state, you go through the same decision process. In this case, you decide you will make a measurement. And then you basically, if you make a measurement, you get to observe what the soil moisture level is, and so on. Okay? This is a picture of, this is an illustration of what the policy is. By doing this, we can reduce the sampling rate by about 10 to 20 points, in the sense that we get very good estimation accuracy by going from originally once every 10 minutes to about 1 to 2 hours. The problem with, there is a weakness in this approach, which is the quantization rate. Because of the computational barrier, we have to quantize the soil moisture levels into no more than a dozen states. So think of 0% to 100% soil moisture level, and you quantize them into 10% increments. And that is a quantization noise that you introduce for numerical reasons, but you cannot remove. So later on, we actually also looked at an open loop approach using successive sampling that actually can improve the performance in the estimation accuracy. All right. So this is on, if you have any questions, feel free to actually jump in. This is a short question. So this is the part on how to put different elements together, even though conceptually this is fairly standard optimal control problem. There are many different elements to work through. The second part is on system deployment, and here is, I have a sequence of sort of lessons I would like to share with you. Our original design, this we went through back in 2008 for about 2-3 years. At the time, our priority was to quickly put together a system that would be used. So we decided to use what we consider to be mature technology, in this case, ZigBee. Okay? It gives us multi-hop network that will give me the coverage that I need over a large field. And there are a lot of chips and products already on the market. So we decided to do this. The disadvantage is, for those who know this, the picture here is basically showing these are what's called end nodes, and this is a coordinator, and this is a router node. So the data can be actually transferred from one location to the next and then hop on. The disadvantage is, under ZigBee, the router nodes is not provisioned to be put in power savers. It cannot be put to sleep. And that basically means it will consume a lot more power and need much bigger batteries. And this was for our original design. Our choice was XP Pro. This was Series 2, I think. Everything was encapsulated. This is advantage and disadvantage. There was very little we could reconfigure, and later on we found that to be a major headache. The system itself is pretty small. Two AA batteries and very small mini solar cells, which we calculate to be enough. The routers needed much bigger solar panels, bigger and different batteries. So our first deployment, we did this in a botanical garden next to on the University of Michigan campus. And then our first deployment is actually on some place very, very far away, as you guys are referring to. This is in Kenton, Oklahoma, and very expensive to make a trip as well. We have a team of students. And so we learned a lot from this experience. This is about 90 miles west of Oklahoma City, and why we picked this location, and that is because Oklahoma apparently is considered one of the geographically representative places of North America. Designated by NASA, there's about 8 to 9 such places. Our location is on a cattle farm. We had a team of 8. It took us 8 days. Our goal was to deploy a sort of a grid-ish network. The spacing is about 30 to 60 by 80 meters, and because this is a cattle farm, there's no infrastructure. We decided to place 3 router nodes off to the field of this square shape, and then the base station is powered in. It's attached to a shed owned by the farmer, and that is up on the slope further to the left of the field. Okay. Most of the time, as I said, we spend digging holes because our original mounting solution was viewed as grossly inadequate by the farmers, so we borrowed their farm equipment, and the idea is to dig a hole 6 feet deep. We use these 10 feet posts, 6 feet underground and 4 feet underground and 6 feet above ground, and mount the wireless transceiver module on the top of the post. The completed system, if you can see, this is basically this, as I said, this is the post. The module is mounted here. The QVC pipe is protecting the cable connecting to the soy bush post buried underneath. So they get pulled out and get connected to this box. As you can see, so this is a router module. This is a much bigger module. There are bigger batteries in here and bigger solar panels. Okay. Problems soon emerged. The immediate problem we had was the 3G connection was extremely flimsy. So the 3G connection is between the base station we have and the cellular provider. We use T-Mobile. We tried AT&T, but at that location, T-Mobile is actually better. So the 3G connection comes and goes. The other thing is our own network was unstable. It disappears for hours at a time. It would be operating, and all of a sudden it goes away. We don't know what to do, and then after a few hours, it comes back. And our initial diagnosis was it has something to do with the unstable wireless channel, and using ZigBee, because there is a parent-child association, you have to wait for the thing to time out before the reassociation is established. But because our device is so heavy in duty cycle, they come on for a few seconds and then go to sleep for 10 minutes. Before you know it, a few tries and it's a couple of hours. So that was just, that didn't work out. Later on, in a couple of months, more problems surfaced. The protective cover, we actually put protective covers. They actually travel cows, so this implementation is in the presence of cattle. So they cause a lot of damage to the boxes and the solar panels. They really chew on these things, and they rub against the posts and they dislodge them. Big animals. Well, these are all things when you think back to, well, why didn't you protect them, or what didn't you do it? We were also running out of time in the initial visit. And the battery we used for the router, lithium-ion battery, for those of you who know, these are fire hazards. And we did this in August. It's 110 degrees at least during the day in the field. So they soon gave in. On our second trip, the package cracked open. They were still operating, but we had to decommission them. They would have died very soon anyway. So this didn't work out too well, but it was a good lesson learned. So then we moved on to our second generation. The lessons learned were, I have a picture here that's not showing up. Sorry about that. So what we decided to do is to abandon ZigBee. We decided it's providing a lot of things that we don't really need. We decided to build our own system just using 15.4. So essentially built a 2-layer hierarchy. The lower layer, we have something similar to a local coordinator and the end device. It's a one-hop communication. The local coordinator has 2 wireless interfaces The second interface talks to a base station. So essentially, we have a logical separation between these two hops. One of the lessons we learned from our first generation is multi-hopping is very, very difficult to work with, especially when you have a heavy duty cycle. Things go to sleep, how to synchronize, and so on. So we decided to just separate them into two layers, and then we can write our own protocol on top of it. It's much simpler. The other thing is, instead of using 3G, we decided to use S. And that worked out wonderfully. Much better reliability. The trade-off is a bit of delay, which we can work to live with. The other main lesson we learned is we decided to abandon renewable energy. We got rid of the solar panels. The reason is because the wear and tear on these things here are severe. But the other main reason, if you have ever worked with them, is that the rechargeable battery's quality is nowhere near non-rechargeable batteries. You get much higher dynamic range in operating temperature. And because our system's all outdoors, it just makes a lot more sense to go with non-rechargeable batteries. And because the system's duty cycle is so low, we have been able to basically engineer them to last for a couple of years. Our Kenton sites for the second generation devices, so far they have worked for 1.5 years in total. Okay? So this is also sort of an important lesson that we wouldn't have thought of earlier. An additional advantage of using a non-rechargeable battery is we reduce the noise induced by a voltage regulator, something you have to use if you have a solar cell. And you can see the second system is much cleaner. It doesn't have this noise introduced by the voltage regulator. Since I'm short on time, the other improvement two improvements, we put up protective fence along the poles, and the other thing is we now move the position of the poles, the wooden pole, a few feet away from where the sensors are. The reason is because of disturbance to the soil, a water pocket easily formed around at the base of the post. So when you move away, you cause less disturbance to the soil, so what you measure is closer to what the soil would have given you. Some more recent deployments showing here. These are two deployment sites in Northern California, near Sacramento. This is New Hogan Lake. It's land owned by the Army Corps of Engineers. And in the nearby, around the same area as Second Network, this was all deployed in late 2012. And the generalized vision, this project is called Sourcescape. Our system is called Ripple 2, our second generation. The system now has been connected to the USIF framework, so we have Oak Ridge National Lab on board the third phase of the project. They're handling the data repository. So everything we have collected is actually now retrievable. If you're interested, please visit our project website, as well as the websites managed by the Oak Ridge National Labs or the Mercury, who can basically pull up different data traces that we have. So I basically talked about the overview of the project and two specific aspects of this, and hopefully some of these lessons are useful to you, and here are some references. I'll end my talk here. Thank you.